Okay, should be recording now. So when we're at the sea and you're sitting on a rock, you're dealing with silicate minerals that are made of silicon and oxygen and some other trace metals. The air you're breathing is nitrogen and oxygen, and it may contain bigger particles called amines. That's what gives it that sort of fishy smell. So it's all around us. Atoms are incredibly small. So if a single pebble from the shoreline a single pebble from the shoreline would contain more atoms than you could count in your entire life. The number of atoms in a single pebble exceeds the number of pebbles that you would find in the San Francisco Bay. So there's just lots of atoms. To get an idea of how small atoms are, imagine this. So if every atom were one small pebble in size, the pebble would be as large as Mount Everest. So teeny tiny. So atoms are composed of matter. The properties of atoms will then determine the property of the larger macroscopic matter. So if I have gold atoms, and we accumulate a bunch of gold atoms together, and then we get some matter that's made of gold, it will have the same properties, or the properties of the atoms will be laid out in the properties on the macroscopic scale. An atom is the smallest identifiable unit of an element. So if we took a gold ring and we cut it in half and cut it in half and cut it in half and kept going all the way down, the smallest thing that I could still say is gold would be the atom. An element is a substance that can't be broken down into a simpler substance. So if I have something like gold, I can't break that down into a simpler identifiable substance. Okay, I could break an element down into protons or neutrons and electrons, but the protons from gold are the same as the protons from oxygen. So the simplest identifiable thing would be the element. There are 91 different kinds of elements in nature. So then there are about 91 different types of atoms. I'm breaking up again, losing you again. Oh, this is killing me. Let's see. Yeah, it's going in and out. Okay. I am going to, we're gonna go on a little adventure through my house. I'm gonna go closer to the, to the source. Okay. Yeah. The Wi-Fi is not working. Yeah, I know. I've got to be in here for a couple minutes and lecture because I'm trying to get closer to the router. Can you guys figure something out?
Yeah.
Okay.
You can go outside for a little bit?
Yeah, just give me a little bit. Okay. Sorry, I don't know what's going on with the internet. Yeah. See, I'm a person just like you guys. Yay. Is that better? Yeah, okay. Okay, cool. So we're just gonna chill on my couch. Okay, perfect. So, so like we said, there's 91 different kinds of elements in nature. So there are 91 different types of atoms. And then there are about 20 synthetic atoms. A lot of the heavier atoms on your periodic chart, the ones that like are nameless or have like really funky names, those are synthetic in that we've been able to make them in a lab setting, and they've existed for a really small period of time under very, very specific circumstances. But the exact number of natural and synthetic is still kind of wishy-washy, because some of those synthetic ones that we've been able to make may actually exist in nature, like in really strange environments, like a black hole or near, you know, the surface of the sun or something like that, or after a supernova. So as far as how the theory of the atom evolved, well, back in like 460 BC, Democritus came up with this idea. He suggested that all of matter, because, you know, they're like holding a piece of matter, like a, I don't know, piece of bread, and you cut it in half, and you start to think, okay, well, you can cut this in half. How much can you cut this down? To smaller and smaller pieces, you end up with a really, really tiny indestructible particle. And he gave the indestructible particle the name of atomos. So that's where we're getting atom from. And that means indivisible. So a particle that we can't break up into anything smaller. He was the first person to have postulated that, you know, matter is made up of these tiny little particles. And then, like, nobody really did anything with it until 1808 with John Dalton. And, you know, one of the reasons that we didn't see a whole lot happening between then and 1808 is because the scientific method didn't come around until, you know, 1700s, where we had like oh, you have to prove science. You can't just say something and it's true. So people started attacking all these problems. So here are a couple of the broader theories that came around in the 1800s. So each element is composed of tiny indestructible particles called the atom, which is similar to what we talked about. All atoms are a given element, or all atoms of a given element have the same mass and same properties that will distinguish them from other elements. So, hold on one sec, just checking on time. So all of the atoms of gold are going to behave like gold. All of the atoms of oxygen are going to have similar masses and behave like oxygen. Those two, you know, they may have properties that are similar. They don't. Gold and oxygen do not. But some things may have properties that are similar, but there's always going to be these distinguishing qualities. And then the third one there that's sort of hidden is that atoms combine in simple whole number ratios to form compounds. So you're never going to get half atoms. You're never going to get like carbon mixed with half of an oxygen. It's always going to be whole numbers. All right, so I'm going to talk about that. Okay, so a little bit later on, like 50 years or so, 60 years, Thomson, this physicist, sort of was able to break down the atom into smaller particles. So the first thing that was actually discovered was the electron. And he found that when he ran a atom through this sort of cathode setup, that he was getting an electrical charge or a negative charge. So he discovered the electron. So the electron had a negative charge. It was much smaller than and lighter than the atom as a whole, really had almost negligible mass. They're present in all substances. So he didn't see it in just one type of atom. He saw it in all the atoms that he used. And so he decided that there is a series of electrons, and then they are sort of stuck in this positive cloud, or this sphere of positive charge, because all atoms, when they're in ground state, have a neutral charge. So if we found a negative particle, we need something equal and opposite to balance out that negative charge. So he thought that there was a positive sphere that it sort of sat in. And this is where this idea of the plum pudding model comes into play. I guess they ate a lot of plum pudding. So I guess the sphere is the plum or the pudding, and then the little electrons are the pieces of plum floating in it, which sounds disgusting, but it is what it is. So a little bit later, Rutherford ran this experiment. It's called the gold foil experiment. And he had a source of alpha particles, probably radioactive lead or something. And it shot these little alpha particles at a thin piece of gold foil. And this gold foil was like, 2 atoms thick, 3 atoms thick, super, super thin. And what he postulated was that these alpha particles, because they're really high energy particles, they should just go straight through because the electrons were super teeny tiny. So the electrons wouldn't interfere with the alpha particles, and then the positive plum, the pudding stuff, the positive sphere wouldn't affect it either. So he would expect it to go straight through. Well, he had this receiving paper that lit up every time a particle hit it. And what he saw was that some of them did in fact go straight through, but then he was finding other alpha particles were actually deflecting. Some were even like getting repelled back almost in the direction that they came from. So this is what he had expected to happen using the plum pudding model. That didn't happen. The alpha particles didn't go straight through. He had some deflection. And so what he ended up coming up with was the nuclear theory of the atom, or that there is a nucleus in the center of our atom. And in the nucleus, we find protons and neutrons. And then there's a sphere of electrons around it. So some of the nuclear theory postulates, most of the atom's mass and all of its positive charge are contained in the small core called the nucleus. So 99.9% of the atom's mass is sitting right here. And it's getting a positive charge from the proton. Protons are positive, neutrons are neutral, and then the electrons are negative and they're floating around. So most of the volume of an atom is empty space. And then we have these really teeny tiny negatively charged electrons that are dispersing through it. And then the number of negatively charged electrons outside the nucleus should equal however many protons we have inside the nucleus to keep it charge neutral. So if you have 6 protons, you should also have 6 electrons. The neutrons can vary, and we'll talk about that when we get to isotopes. So this is a much different theory. What we end up seeing is that our atom is really just a majority of empty space. And when we break up these little particles, so protons and neutrons and electrons, what we end up finding is that they are contained, or within them, they contain mostly empty space and a small amount of matter in the form of quarks. And if we break those up, we find that they're made up of mostly empty space. And one theory is that when you get to the root of it all, the most fundamental thing is empty space and a vibrating ring of energy. That's called string theory. So that the idea is that we actually don't have any solid matter, that all matter is space and vibrating energy, which is pretty cool. They don't know for sure, but it's a theory. So the dense nucleus makes up 99.9% of the mass, but occupies only a small fraction. Electrons are distributed through a very big region. Hello. Matter at its core is much less uniform than it appears. So we always have this idea of, running our hand over something and it feels solid or it feels like it's continuous, but that's not actually the case. There's little bits of matter and then lots of space, and little bits of matter and lots of space. Interesting, if matter were composed of just atomic nuclei piled up on top of each other like marbles, it would be incredibly dense. So if we didn't have that really low volume electrical cloud, we'd have a very dense situation. It says a single grain of sand composed of just nuclei, so small space, would weigh about 5 million kilograms. So super, super dense. they do believe that you can get things like this where you have almost just nucleus stacked on top of each other in black holes. You get these really dense matter. Size proportion. So if we were looking at a proton and or a neutron being the size of a baseball, an electron would be a grain of rice. So it's about 2,000 times different in their magnitude. As far as the charges are concerned, well, you may already sort of know this, but different things will attract each other, right? So positive charge, negative charge will move towards each other, or opposites attract. Likes repel each other. So positive and positive will spread away from each other. Negative and negative will also spread away from each other. You may be thinking, well, how can two protons, if they're both positive, sit inside the nucleus next to each other? Simple question with a extremely complicated answer that I have like only sort of understood through some really advanced physics books. So there's like a gluon force field. It's very, very complicated. But for now, we're just going to say that the protons sit next to each other, even though they're positive. The electrons, on the other hand, those guys will repel each other. And so that's why they always are like spreading out within the electron cloud. So 1 positive plus 1 negative will give us an overall charge of 0. You don't need to know these. You don't need to know these, but here's just a general idea of the size. So a proton has a mass of 1.6 times 10 to the negative 27. That's a lot of decimal places out, kilograms. Electrons are about 2,000 times smaller than that. As far as in reference to the AMU scale, a proton is about 1 AMU, a neutron is also about 1 AMU, and an electron is 0.0005 AMU. So electrons don't have much of a charge, or don't have much of a mass, but they do pack a big punch. They have a charge, and that charge is important, especially with chemical bonding. So you want to know the charges. And that will become second nature, hopefully, as we move through the semester. As far as lightning is concerned, you get, just for your information, you'll get a negative charge buildup in the clouds, and you get a positive charge buildup on the ground, and it's trying to create a charge neutralization or equalization. So the negative and positive charges will come together through lightning. That's what's happening there. So rebalancing of the charges very quickly, intensely. So how do elements differ from one another? So here I've got helium, and here I've got a can of aluminum. So elements are always going to be defined by the number of protons that they have. That is what makes an element an element. If it has 2 protons, it is helium. If it has 13 protons, it is aluminum. 6 protons, carbon, so on and so on. Neutrons can change, electrons can change, protons can't change. If you change the number of protons, you've actually changed what the material is. So the number of protons in the nucleus of an atom is known as its atomic number, and it's given by the symbol Z. When you're looking at your periodic chart, that whole number that's at the top, that is the atomic number, okay? We start at 1 with hydrogen, and then just like a book, you can read it across 1, 2 is helium, go down to the next line, 3, 4, 5, all the way until we get into the low hundreds for some of those synthetics. So when looking at this, go ahead and see if you can find sulfur. And then we'll identify how many protons sulfur has. Sulfur has 16 protons, all right? We look for what has 56 protons. That would be, so you just find 56, that would be barium. We look for krypton. Krypton is 36 protons. That's one of our noble gases. Okay, so just starting to get comfortable with where those are. Some periodic charts have the names on there. Some of them don't. Like my periodic chart just has the symbols, but I know them pretty well. I'd recommend for you getting yourself a periodic chart. I think the one in the lab manual does have the names on it. Get one that has the names on it. Just give yourself a break this semester and learn them another time. All right, so here is our periodic chart. Let's look at some of the other things that we've got on there. So it's highlighting beryllium, number 4. So 4 means it has 4 protons. That's its atomic number. You'll see the symbol Be. Again, some periodic charts just have the symbol. Some of them will also include the name beryllium. Then you have this thing right here, this decimal number, that's the atomic mass. And it is the total mass of the atom. And you would think, oh, shouldn't that be a whole number? Well, you would think so, but there are, there are different isotopes that we average together that give that a decimal number. And we'll talk about isotopes in a little bit. So we change the number of neutrons. So as far as the symbols and the names, most chemical symbols are based off of the English name. But we are such a self-centered society. We think that they all should be based off of our language, and they're not. Some of them are based off of Latin. So lead, for instance, is not L or LE, it's PB, because its Latin root or Latin name was plumbum, which sounds kind of funky. But if you've ever done any construction before, a plumbum is a really heavy weight tied to a string that you can get a true top-bottom measurement. Mercury is Hg. Iron is barium, Fe. So, you know, just knowing that some of these.
We're having art.
You're having art, okay. I'm finishing up teaching, okay.
But we're supposed to look at these reasons.
You give me a couple more minutes, Gab. Brittany, I just need like 12 more minutes. Okay, thank you. Life. So crazy right now. So crazy right now. All right. So some of the elements are named after like properties. So argon, for instance, is named after the Greek Argos, which means inactive. And argon is under the noble gases, and those guys tend to be inactive. They don't like to bond with things. Other ones are named after countries. America. Awesome. Okay. There's all sorts of different things. Some of them are based off of people. So Marie Curie, who did a bunch of work with radioactivity, she was a pretty awesome lady. And there's actually a movie that just came out or is coming out on her. So curium is for her. Bromose, again, properties. So bromose is for bromine, which is stench because it's kind of stinky. So as far as patterns are concerned with the way that this periodic chart is laid out, it was laid out by a gentleman named Dmitry Mendeleev, who was extremely smart. You can see the picture of him here. He looks very smart. He was also like very troubled man as well, which usually tends to be the case. And what they said was he had all these, like a deck of cards filled with, or each one had a different element on it. And he was on like a train going like Trans-Siberian or something. And he was playing around with the deck of cards, trying to figure out like an ordering for the periodic chart, because the periodic chart wasn't invented yet. They just had elements. And so he started arranging them in different orders. And one way he did it was by their relative mass. And he started to see that when he laid the cards out, that there were sort of similar properties. So you'd get, you know, well, hydrogen did its own thing. Hydrogen does its own thing, but we'd get helium would behave in a green way, and lithium would behave in a pink way, whatever that property is, and beryllium would behave in an orange way. And then we had sort of varying properties. And then he found that there was a repeat of that green, the pink, the orange, so on and so on, over and over again. And so what he decided to do is, well, once the pattern repeated, he truncated it and stuck it underneath. So when he saw that, oh, sodium, there's my pink, it's a repeat of what's happening over here, I'm gonna stick it underneath sodium, or I'm gonna stick sodium underneath lithium. And so we start to see that this thing gets cut and put into the periodic chart form that we have now. So in this way, columns on the periodic chart have similar properties. All right, so let me move this out of the way. Lithium is much more similar to potassium all the way down here than it is to beryllium, its neighbor. All right, so things in the same column behave similarly. So all of this was based off of observation, which is really cool and crazy. I mean, to think about coming up with this, you know, like for us, it intuitively makes sense now because we're looking backwards, but for him, he had no format for laying this out. So that's pretty awesome. But as far as why it's organized this way, why there are similar properties, we're going to talk about that in chapter 9 when we get into electrons. For now, you're just going to take my word for it that column 1 behaves similarly, column 2 behaves similarly, so on and so on. All right, so periodic chart. So if you want, you can start coloring on your periodic chart or drawing on it or whatever. But here, normally when you guys take a test, if it was traditional, you'd get a fresh periodic chart for your exam, but you guys get to use your NoteUp periodic chart. So Merry Christmas. So the first thing I'm going to put on there is the zigzag line. So you can see it here underneath the H. It comes by the B, the SI, the AS, TE, AT. Okay, it may already be on your periodic chart. If it's not, put it in there, or if you want, you can highlight it. That zigzag line is the separation point between metals and nonmetals. So everything to the left and down of that we classify as a metal. Anything to the right and up of that is considered a nonmetal. This periodic chart has the lanthanides removed from it. So if you go down here, you can see that we go from 57 and we jump to 72. We're not just missing those elements, they're just down here. All right, so there's 58 to 71. It would get stuck in there and you'd have another sort of step down like we have here, step down, we'd have another step down at this point here. The reason they don't stick it in there like that is just because it wouldn't fit on a piece of paper very well. We don't spend a whole lot of time with lanthanides, but just know that that's where they're going. So we've got a lot of metals. Most of the elements that we actually have, we would classify as a metal. Some of them you may not realize, sodium is a metal. Now sodium chloride doesn't behave like a metal, right? Because it's a compound. But sodium on its own is a metal. All of these guys metals. We've got what we would consider our nonmetals, pretty easy, like the noble gases, obviously not a metal. Fluorine, oxygen, nitrogen, carbon, those guys don't behave like metals. And then right in the middle, we have these things called metalloids. Those have qualities of metals and, just checking on time here. Qualities of metals and nonmetals, which is sometimes they're called semiconductors, and they're really, really useful in electronics. So silicon, like we don't call it, you know, Copper Valley, we call it Silicon Valley because silicon is a really, really useful material for electronic devices. So some properties of metals. Metals occupy the left side of the periodic chart and have similar properties. Metals all tend to be good conductors of heat and electricity. They're easy to flatten into sheets or draw into wires. They're shiny, lustrous. What's another thing? They tend to be solid. There's only one metal that's not solid at room temperature. Does anyone know what it is?
Mercury?
Mercury, yeah, mercury. So I'm not old enough to have played with mercury thermometers as a kid, but my mom used to say they'd break them open and play with those. And I was like, Mom, no, that stuff's so bad. So this is the important thing here. Metals tend to lose electrons when they undergo chemical changes. Okay, so if you want next to that or in your notes, you can say metals form cations, C-A-T-I-O-N-S. Because of the setup of their electrons, everything wants to become like a noble gas. So it's much easier for metals to give up electrons than it is for them to take it on. If you give up an electron, you become a more positive particle. All right, I think of electrons as like those negative people in your life. If you collect a bunch of negative people, you become more negative. So if you're a metal, you're going to lose some of those negative people. You become more positive. Examples: iron, magnesium, chromium, all those guys. Okay. Non-metals, the things that are on the right side of the zigzag, have much more varying properties. Some are solid at room temperature, some are gas at room temperature. They're poor conductors of heat and electricity. We don't use oxygen to conduct heat or electricity. Important thing here, nonmetals tend to gain electrons when they undergo chemical change. So if something's losing electrons readily in the universe, something has to be gaining it. Otherwise, we're just gonna have all these electrons floating around. So nonmetals tend to undergo electron gain, which means that they form an anion, A-N-I-O-N. Anion meaning that they have a negative charge. Nonmetals like oxygen, nitrogen, chlorine, and iodine. All right, then we've got the metalloids, which are along the zigzag, our semimetals or our semiconductors. Intermittent electrical conductivity, which can be, we can change or we can control their electrical conductivity. So they're a lot more useful with electronics or delicate electrical products. Silicon, arsenic, germanium, all good metalloids. Silicon over here. Okay, so within the periodic chart, we've got our metals and our nonmetals. Now we're going to distinguish between main group elements and transition metals. So main group elements are column 1 and 2, and then the 6 columns on the right-hand side. So there are a total of 8 main group elements. It's the guys that are sticking up higher than the other ones. Those have very predictable properties, predictable charges. We like working with the main group elements. These guys in the middle that are known as transition metals are a little icky. They do weird things. They have varying charges. They don't always behave consistently. So just less predictable. So as far as the different groups are concerned, column 1, these are known as the alkali metals. Column 2 are known as the alkaline earth metals. These are just transition metals. Then we have 3, 4, 5, 6 are the chalcogens, I think. I don't know. I don't even remember that one. But 7 is the halogens. So you do need to know the halogens. And then 8 are the noble gases. If you want to write that above yours, you can. And then I'm going to have you guys write some things above each of these as well. So for column 1, I want you to put +1. That's because everything in column 1 likes to form a +1 charge, or they give up 1 electron. Column 2 here, I want you to write a +2 charge. They form a +2 by giving up 2 electrons. For column 3, really it only applies to aluminum. I want you to put a +3 charge. So aluminum gives up 3 electrons consistently. We'll skip 4 for now. 5. I want you to put a -3. So nitrogen and phosphorus really are the only ones sort of that apply to that, but they like to take on 3 of those negative electrons. Over this one, we're going to put a -2 charge. So oxygen, sulfur, those guys like to take 2 electrons on. Any guess what the halogen would be? -1, yeah, -1 charge. And then over the noble gases, you can put like a 0 or a 0 with a strike through it or something, just to let you know that those in general don't form ions. They don't form charge. Why? Their outermost electron shell is completely filled. So they have all the electrons that they would want. So they're just happy the way they are. So they don't want to bond or do anything. Oh, 916. Okay, so we're done. So we'll finish this chapter up on Wednesday. And yeah, that's all I got. Okay, if you have a question, feel free to stay around and we can chat. I'll try and get these lectures up sometime today or tomorrow. All right. Sorry about the fallout there, but we made it work. So good job. Thank you for the help. Bye, guys.